At just 728 square kilometres, Singapore is the second most densely populated country on the planet, where infrastructure needs to keep pace with 5.5 million people. At the top of the agenda is a new sports stadium worthy of a world-class reputation.
We need a facility to enable us to host world-class international sporting and entertainment content. At the same time, it has to be multi-purpose given our land constraints and the need to optimize every available acre of land.
But in Singapore's unique environment, space to build isn't the only problem.
So we are 1 degree north of the equator, which means that we are warm and humid, and we have rainfall almost 1/3 of the year. So the stadium has to provide protection against the weather so that we are able to continue with the programming regardless of the weather.
To take on this colossal challenge, engineers have created a structure like no other on Earth. This is the Singapore National Stadium. A gigantic multi-purpose sports arena.
The National Stadium is currently the largest dome structure in the world. It's really mind-blowing.
I think the engineers have achieved something which is truly incredible. Everything from the smallest boat to the entire freestanding dome is a work of wonder.
It's a huge achievement in terms of engineering and design solutions, and it's all about integration of architecture and engineering working together.
Four A380 passenger liners placed wing to wing would nearly fit inside this megastructure's 310-metre span. 8 gigantic arches create an 82-metre-high freestanding shell with enough space inside to contain the Sydney Opera House. 50,000 spectator seats can be increased to 55,000 by an advanced reconfiguration system. And at the push of a button, 2 gigantic roof leaves, each 10,000 square metres in size, will close to protect from Singapore's turbulent weather conditions. The largest free-spanning dome the world has ever seen marks the dawn of a new age of superstructure.
This is an amazing vantage point. You get a fantastic view of the field of play, as well as the entire bowl. And if you look over on that side towards the west end opening, you can get a glimpse of the cityscape.
It's down to Stadium CEO Lionel Yeo to oversee this one-of-a-kind arena.
Well, think about the scale of the project. You have a dome which is this size, 310 meters wide, 82.5 meters high. I think it is an engineering marvel. It's a very complex project.
The domed roof in particular makes this stadium a unique challenge. Engineer Max Sui Chang was part of the team responsible for its construction.
The dome is really a very iconic structure here in Singapore. If you look across the city skyline, you can definitely see it. So 9,000 tons of steel was used to carry this roof above me right now. This is definitely one of my most complicated projects that I've ever done.
The team have constructed a record-breaking piece of engineering. But how do you erect a structure to stand strong with no columns or supports?
The dome wants to flatten out. That's the nature of a dome. You really need to prevent that from happening.
And how can you transform an enormous stadium to accommodate huge concerts and sports matches?
The National Stadium will need to cater for various events, and it's not an easy task to move such a structure, considering the massive size.
As well as taking on Mother Nature.
It rains a lot and it rains hard. But the stadium's design calls for this open roof that needed to provide a serious amount of shading and protect the spectators from the rain.
Creating one of the world's largest multi-purpose facilities requires engineers to radically rethink every aspect of stadium design. This is the Singapore National Stadium. A record-breaking dome, the likes of which the world has never seen. 250,000 cubic meters of concrete has been poured into this megastructure, creating a 275,000 square meter floor area, large enough for an enormous seating bowl, capable of accommodating 55,000 spectators. But to encase this vast amphitheatre, engineers like Max Wee Chiang needed to create a colossal roof that could support itself.
The seating arrangement that was designed by the architect leaves a very massive space for engineers to design a roof that covers it. With columns, you'll be obstructing the view of the spectators. So it's quite critical to have the columns removed.
So to preserve spectator visibility, the team have come up with a remarkable form that requires no columns at all.
To support the dome of this scale, the solution is to have a three-dimensional rib truss system. What we have here is 6 runway trusses that runs from left to right. And then you have at 90 degrees 2 transverse trusses running across to brace it up. In addition to that, we have diagonal trusses that connects the corners together to form a very three-dimensional stiff structure that's able to withstand the huge load that it's experiencing.
An arch is one of the strongest shapes under gravitational load. So combining the 2 transverse arches with the 6 runway arches creates a 3-dimensional arch, or dome. Strong in all directions, it takes the gravitational load to the ground.
Once you arrange the trusses in a 3-dimensional way, you really get a very, very stable structure. It's really the most efficient way to channel all the forces down. It kind of reminds you of a rib cage. And as you can see, thanks to the dome structure, the spectators really get a very good view of the event, just simply because there are no columns.
During construction, giant cranes erected the steel truss, while 90 temporary pylons supported the structure from beneath. After 9 months, the final piece was raised into position. The temporary pylons were removed, and the truss rib cage could finally support itself. But with the framework in place, engineers face another problem.
The Singapore Stadium, in fact, is built on reclaimed land, which essentially is Singapore marine clay. And Singapore marine clay is like butter. It is almost impossible to be supported on. So the 3-dimensional dome really wants to flatten out. And the challenge for us is to find that solution to prevent that from happening.
To keep the truss from spreading and collapsing under its own weight, the team must turn to the great architectural pioneers of the past. Deep in Orange County, Indiana, architect Todd Rotman is exploring a region that draws visitors from around the globe.
This is what started it all, the mineral springs.
The secret to this area's popularity can be found in its artisanal waters.
People thought the water here had medicinal qualities, so people would drink it, they would bathe in it, and this ended up becoming a playground for the rich and famous. The draw to this area was enough to make the owners want to build a hotel resort that could rival even the finest spas in Europe.
Tasked with making this dream a reality were architect Harrison Albright and bridge engineer Oliver Westcott. In 1902, they revealed a building that changed the world of structural engineering.
Oh, wow. That is gorgeous.
This is the West Baden Springs Hotel.
It's just so huge. It's amazing.
And its crowning jewel, a gigantic freestanding dome sitting high above the atrium.
At the time, it was the largest dome in the world. Over 130 feet tall in the center point, over 200 feet in diameter. What makes this amazing is the technology and the engineering that went into making it possible, because it hadn't been done before.
In the absence of a central column,
What an amazing view.
how did the engineers keep this immense structure up?
So if you look up at the roof, you can see 24 steel trusses that terminate at a drum in the middle and extend down and out to the columns along the perimeter. The problem is there's a lot of weight being pushed out on them. So to take that load, pushing out, they put 2 steel tension rings around the perimeter. So if you look out across the dome, above and below those windows are those tension rings, and those are structural components that hold this building up.
But to demonstrate how the inspired tension ring beam solution works, Todd has scaled it down.
We've got a simulated dome structure with the trusses. We've got a weight. Let's put the weight on it and see how the trusses hold up. So as you can see, the ends of the trusses kicked out. There was nothing to hold them in place, and we've got a failure. Now, if we add a tension ring around the perimeter of it, and we use the exact same trusses, let's see how the tension ring helps. No failure. It's able to support the weight. And we can even put additional weight, and it still holds it. The tension ring is taking all of that lateral force, it's containing it, and making all of the load go straight down. So imagine the innovation of making one out of steel and supporting a 200-foot diameter dome. It's a simple concept, but used in a big way.
Albright is rumoured to have been so confident in the dome's design that he stood on top of it as the construction supports were removed. To get a closer look, Todd is braving the climb to an area very few people ever get to see.
All right, here we are, up on the roof. Whew, yeah. But this isn't our final destination.
At the very apex of the dome, its trusses are tied together in a central drum structure, suspended high over the hotel lobby.
All right, so this, to me, is a little bit more scary than being on the roof. These boards date back to 1901. You know, this is kind of where the structure starts, right? This is where it all comes together, and from here the forces go out down the trusses to those tension rings.
And being here, with no supports between the drum and the lobby floor 200 feet below, is only possible because of those incredible tension rings.
I'm still a little freaked out. So looking down the hatch, we can see original wire glass pendant that decorates the ceiling of the dome. Yeah, this is pretty amazing. You can see the bottom of the drum.
With the world's largest freestanding dome as its showpiece, the hotel attracted visitors from around the world. More than a century on, the domed roof has stood the test of time, thanks to its ingenious tension ring support.
To build this magnificent structure with such a large dome, it's just a testament to the incredible engineering. It's truly awe-inspiring. Here we are today, over 100 years later, same structures in place, still standing tall, just as beautiful as it ever was.
In Singapore, engineers have taken the same concept and supersized it. The only way to hold a world-beating dome together is with the planet's largest tension ring beam.
So the ring beam is positioned below the trusses, and it is actually somewhere behind these walls. So the ring beam is 6 meters in width and 1.5 meters in depth.
Taking 6 months to complete, the gigantic concrete ring has a circumference of over 1 kilometer encircling the stadium. "10,000 cubic meters of concrete are reinforced by 14 steel tendons, which are threaded through the ring beam and tightened, squeezing it in towards the center like an elastic band. As the weight of the dome tries to spread out, the ring beam pinches back in from 360 degrees, holding the structure in place. Buried in the foundations, the largest ring beam on the planet is hidden in plain sight.
Most people will just walk by and not notice the ring beam because it's actually quite cleverly designed to be integrated with the jogging path next to me over here.
It may not be visible, but above ground are the final components that tie the system together.
So the forces from the arches actually comes down the truss and then hits the truss block. And there are about 20 of these truss blocks around the length of the ring beam. The truss block will transfer the forces down to the ring beam. And there's a lot of things happening at the truss block. Forces in all directions will interact and work the truss block quite hard. So it's very critical for us to design this to withstand the tremendous weight. And we need to introduce reinforcement.
175 metal studs tie the foot of each arch to the thrust block's reinforcing steel rods, transferring the force of the dome's weight into the ring beam and holding it firmly in place. A 120 years since West Baden held the record for the world's largest dome. Singapore has taken that mantle with a structure Albright and Westcott could have only dreamed of.
So the ring beam is actually a very crucial and clever idea to withstand the forces coming down from the dome.
Singapore is one of the busiest city nations on the planet, with an appetite for building big. It's here that engineers have created the Singapore National Stadium, one of the largest sports and entertainment venues on Earth. The colossal roof encases over 3 million cubic meters of completely open space. That's enough room for the arena to be filled with water from 1,200 Olympic swimming pools. But to succeed as a multi-event venue in Singapore's sweltering climate, engineer Scott Monroe and his team need to stay cool.
It's hot and humid all year round, 33 degrees, 34 degrees every day. You put 55,000 people in a place like this, you basically raise the temperature by about 3 degrees. Spectators are sticky, it's uncomfortable. You sit through a 2-hour show, it's a chore rather than enjoying the event. But the roof is 80 meters high, 20 stories. It's a large volume. You can't cool all of that space.
Instead of attempting to chill the enormous room, engineers came up with a more bespoke solution.
We can cool the venue much more energy efficiently from below. So we deliver cool air at around 23 degrees, just under the seat. So we create a comfort zone, a bubble. It's also about managing the venue flexibly. So in total, we have 116 separate zones. We can turn on and off each of the 116 zones individually. So we can scale up and down according to the way we manage ticket sales for an event.
But to deliver localized cool air to each seat, it first needs to be chilled by a subterranean climate control system.
This is the heart of the system. We're producing chilled water in here at 8 degrees. We push that chilled water out to the stadium. It goes through an air handling unit associated with each zone of the bowl cooling system. The chilled water arrives there at 8 degrees. We pass air across the cooling coil, provides the cooling to the seats.
But huge events filling the whole stadium require a cooling system that can handle the high capacity. Deep in the subcellars are 4 500 cubic metre tanks. Each one contains 300,000 glycol balls, a material chosen for its thermal storage properties. These balls are frozen so that as water flows through, it's chilled before being delivered to the seating galleries, and then re-chilled as it is recycled through the system, meaning it's more than able to cope with a full house.
It's pretty fabulous, really, when you think we can sit here and we can air condition 55,000 seats. We put the spectators in a space which is really quite enjoyable. You can sit here for 10 hours in the day and you not raise a sweat.
But this tropical country is also short on space. Randall Lim's team of engineers face another challenge to minimise the footprint with a multi-purpose arena.
We have events ranging from track and field to concerts to football. For a football event, you want to be seated as close as possible to the pitch. And then for a track and field event, you want to be seated as close as possible to where the runners are. For a typical stadium where you have the pitch surrounded by the track, you could be as far as 50 meters away to the pitch. It is crucial to find a solution to design a stadium that caters for various events.
To keep spectators close to the action, no matter what the event, the team must look to the past for inspiration. Since the dawn of spectator sport, stadiums have been bespoke to the event. In the 8th century BCE, the first Greek stadiums were long, narrow, horseshoe shapes, perfect for the Olympic foot races. But the Romans' bloody gladiator contests required an enclosed amphitheatre, like the 157-foot-tall Colosseum. By the time the Middle Ages rolled round, jousting ruled the world of sport, needing a long, straight viewing gallery. But what all these purpose-built venues lack is versatility. In the tropical paradise of Hawaii,
It's so beautiful here. I love living in Hawaii.
engineer Keenan Koga is searching for the answer.
Having this awesome weather here and great environment makes a lot of sense for Hawaii to try to host a lot of different sporting events, but there's not a lot of space here to actually do that.
On an island where space to build is limited, sports fans need one venue to serve all purposes. But in the world of sport, not all arenas are equal.
A football field is a rectangular shape, and a baseball field is a diamond shape. So if you're watching a football game in a baseball stadium, the fans way out here in left field can't see the action happening on the football field over here.
Charged with finding a solution, architect Charles Luckman hit a home run. In the 1970s, he came up with a design that would change the world of stadium engineering.
Well, here we are, guys.
This is the Aloha Stadium,
This place is massive.
an enormous superstructure affectionately known as the Metal Mecca.
You just imagine this whole place packed with fans, everybody's cheering, stomping all over the stadium, feeling it shake. And it may not seem obvious at first because of the size of the stadium, but this place can actually move.
The curved sections at the far ends of the field would remain permanently locked in place. But the flanking seats, divided into 4 sections, could pivot to create an open-sided baseball diamond or a closed rectangular football field.
So if you can imagine, this is where the stadium would part like the Red Sea and move in its given direction. If someone didn't tell you that these sections could move, you would never know.
But to shift 28,000 seats weighing over 6,000 tons was a huge task.
Watch your head.
So Luckman installed clever devices underneath the stadium to make the heavy stands float on air.
So underneath each one of these beams, you had an air skate, which is essentially like a little balloon. The compressed air is filled through this line up here and funnels down and gets distributed to each one of the air skates. And that balloon fills up, and there's a box around that balloon that allows the compressed air to funnel directly down and push this piece up.
To move this colossal structure, 416 of these air skate discs are distributed across the stadium. Feeding them with a constant flow of air pressure creates a thin, frictionless film between the skate and the ground, requiring the force of only 1 pound to move 1,000 pounds of weight. And to see this concept in action, Keenan has taken up another sport.
So here we're trying to illustrate the actual stadium. When the air hockey table is off, there's a greater amount of frictional force between the table and the stadium. So to remove the human factor of the amount of force that I could actually insert onto the stadium, we'll use a piece of paper here, and we're trying to move this piece into the stadium, move it around, change the configuration, but we can't really do that just because of the amount of frictional force that's keeping this piece in place. I can't move this at all. But as you can see, when you turn the machine on, it's mimicking the air skates in the stadium, creating a very small gap between the piece and the surface, which is decreasing the amount of surface tension and friction. So therefore, you only need a small amount of force to actually move the stadium. And now we can actually guide this piece into place, similar to our stadium.
Between 1975 and 2007, the stadium would be transformed twice a year, each reconfiguration taking up to 2 weeks to complete. Weighing 14 million pounds, the Aloha Stadium's movable stands were once the heaviest load to ever be carried on an air film. After 46 years of use, the stadium's days are drawing to a close.
It's really quite an honor for me to be one of the last few people that are standing here before demolition crews start to begin work on this stadium.
But thanks to Luckman's initiative, its engineering legacy lives on.
What they did here is they took a simple concept and blew it up on an enormous scale. The concepts applied here have provided inspiration to so many modern stadiums around the world.
For the next generation all-purpose venue, engineers have adapted the Aloha Stadium's pioneering technique for the 21st century. But this auditorium doesn't just move. It can grow its capacity from 50,000 to 55,000 spectator seats.
The lower tier, so you see behind me, will shift outwards towards the pitch area, creating a void between the lower tier structure and the building, and then the concourse platform will be lifted up to fill the void in between.
To transform such a massive structure
Be careful of the track.
takes some incredible engineering solutions.
We are now underneath lower tier structure. Each tier weighs around 900 to 1,500 tons. There are 3,000 seats in each of the lower tier sections. So in total, we have 8 sections, and that gives us over 24,000 seats to shift.
Just like with the Aloha Stadium, the Singapore engineers have employed a similar device to move their seats.
So these are the front sets of loading points. Before the shifting, we will slide in this, what we call the air skids. Compressed air is pumped into this distribution module, where we will distribute compressed air to every single air skids to lift the structure slightly and also to reduce its frictional weight.
Reducing the ground friction of these immense seating tiers allows just a handful of engineers to push the 1,500-ton structures closer to the action. leaving a void between the stadium wall and the seating tier,
Okay, watch your head.
which needs to be filled with 5,000 extra concourse platform seats.
Okay, where we are in now is a trench that runs across the stadium. It's underneath the concourse platform. And the trench is built for sole purpose for the concourse platform handling machine. This machine will lift the concourse platform upwards to fill the void between the two structures.
This innovative machine performs like a scissor lift, but instead of hydraulics, it's driven by rigid chain technology. In the lowered position, the flexible chain is coiled up for storage. But when driven upwards by the rack and pinion motor, the chain links lock together to form a rigid column. And thanks to even more air skate technology, this 70-ton machine can be moved by just one person along a track running the length of the trench. Meaning only one of these devices is needed to transform the whole middle-tier concourse.
And once in position with the concourse platform secured, the machine itself will lower and will move to the next location to perform another shift. This is definitely a remarkable machine, given its capability to raise up to 95 tons of weight and have a lifting height of almost 10 meters. Without this machine, lifting of the concourse platform is not possible.
With this system in place, engineers have created one of the world's most versatile stadiums. Able to accommodate 50,000 spectators for athletics, and grow to seat up to 55,000 for football and rugby, all while keeping the fans close to the action.
To have a retractable seat system that can shift over 24,000 seats and 14,200 tons of weight is definitely mind-blowing.
The Singapore National Stadium. The largest freestanding dome on the planet. And one of the most versatile sports and entertainment venues ever constructed. But in a city renowned for its unpredictable weather, engineer Randall Lim and his team need a structure that can adapt with a moment's notice.
Having an open-air stadium allows natural light and fresh air into the stadium. However, there are also downsides to having an open-air stadium. The stadium internals and the spectators will not be shielded from the harsh weather in Singapore.
A clear day in Singapore can see temperatures of over 30 degrees, when the stadium's occupants would benefit from a view to the heavens. But at the drop of a hat, everything can change.
The thing about Singapore weather is that a typical storm will change in minutes. We do experience heavy downpour and we get as low as 100-meter visibility.
Immense storms can bring flash floods, and Singapore's annual rainfall exceeds 2 meters. In an unpredictable climate, neither a closed nor open roof will do the job.
From an engineering perspective, the solution is definitely non-negotiable. It has to be a marvel of structural engineering.
To find the best of both an open and closed stadium, inspiration might be found with the innovators of the past. At one of Britain's oldest scientific institutions, historian Louise Devoy is in search of a groundbreaking structural innovation.
This is the Royal Observatory at Greenwich, the historic home of British astronomy, navigation and timekeeping. It's world famous as the basis for the International Time Zone system.
To stay ahead of the curve as a world leader in astronomical study, in the 1880s, the observatory procured a new telescope. But this instrument's enormous size caused a problem.
The astronomers wanted to reuse the existing dome that rose up directly from the building, but the new telescope was too long, and so a new design had to be found.
For Astronomer Royal William Christie, the solution was crystal clear. He came up with a revolutionary proposal to house the new instrument. This is the Great Equatorial Dome.
Wow, certainly worth the climb up those steps.
Standing out on the Greenwich skyline, only this unusual onion-shaped bulb could house the observatory's most prized instrument.
Our whole view is dominated by this giant Victorian telescope. Absolutely fabulous. But today we're more interested in the building around it, this wonderful structure. Christie had to develop a design that could expand to 36 feet across, and he came up with this very distinctive onion-shaped profile.
Expanding outwards from the base, the dome is 5 feet wider than the tower on which it stands. But with the telescope protected from the weather, it still needs a way to see out to the night sky.
Oh, it's quite stiff, a bit reluctant at first.
Christie's remarkable solution.
There we go. Wow.
An enormous adjustable shutter spanning the entire dome.
You can just see all the daylight starting to flood into the dome. That's brilliant. So as we open up the shutters to their fullest extent, we can really see the genius of Christie's design, how it extends across the whole extent of the dome, from horizon to horizon.
To create this vast 7-foot wide partition across the roof requires some clever engineering.
It can be operated by just one person turning this wheel. So this then turns up a series of interconnected rods up and across over to this crown section. You have 2 tail pieces supported by a series of wheels on tracks that move together and move apart. So Christie wanted to keep this very simple with the minimal number of moving parts that could go wrong.
And this incredible structure has got another trick up its sleeve. A clever rack and pinion mechanism rotates the dome to the perfect alignment with the night sky.
It's actually quite disorientating to see the dome above your head rotating while you're still stationary yourself. It's truly impressive.
Christie's innovation was ahead of the curve and has stood the test of time, still being used today over 120 years later.
The Royal Observatory wasn't just a place of scientific inquiry, it was also a place of engineering problems and solutions. This telescope really paved the way for Greenwich astronomers to observe double stars and the planets, particularly Jupiter and Mars. And this was all possible thanks to Christie's innovative design for this dome and the retractable section.
In Singapore, engineers have built an adaptable domed roof. And on a colossal scale, to beat the rainstorms before they hit the city.
The engineering solution is to have a fully operational retractable roof that can open and close so that we can host events of various nature.
At the push of a button, these symmetrical leaves will open or close in only 25 minutes. The National Stadium's 20,000 square metre opening is an engineering marvel that Christie could have only imagined. To shift these colossal panels on a curved dome takes some remarkable engineering.
The retractable roof is curved to fit the world's largest spanning dome. And because it's curved, getting them to move is a big hurdle. Weight must be optimized and reduced, while the retractable leaves need to be flexible.
A completely solid structure could get jammed as it traverses the dome. So engineers built a flexible frame and covered it in a pliable material that could be inflated to minimize weight but maximize flexibility.
The movable roof consists mainly of ETFE membrane, and this is lightweight and also allows flexibility in the roof movement. Flexibility is important as we are moving a structure of that massive size.
Keeping components to a minimum, the huge roof panels are shifted by only 16 motor-driven winches, hoisting the leaves along 5 fixed rails on sets of wheels known as bogies.
There are 20 bogies carried each leaf, and total 40 bogies on the entire roof. Each bogie has a 4-wheel contact point to the fixed rail. This minimizes the contact points. When you see the stadium from afar, the entire movable roof looks incredible. The roof is definitely an engineering marvel.
For the team behind this daring project, the engineering achievement is immeasurable.
This project is so groundbreaking because of the sheer size. It's the world's largest freestanding dome, and that makes it quite incredible on its own. This must be one of the most complex engineering projects ever undertaken.
By building on the work of the pioneers of the past, overcoming huge challenges, and pushing the boundaries of innovation.
It is really out of this world, and with the amount of complex challenges that we have faced, the Singapore National Stadium is really a marvel of engineering.
The engineers are succeeding in making the impossible possible.
I often take a step back and look at the stadium in wonderment. It's really quite an amazing architectural achievement. I'm very proud to be part of this project. It's just incredible.